Hey, more probability, huh? We were just talking about what happens if I have independent events. But how do I know? How do I know if they're independent? How would I figure that out? So let's talk about a joint distribution. We'll keep it simple for now, just two events: the x outcomes in the vertical columns and the y in the rows. We want to know what's the probability of these outcomes. If these are independent, like we did before, then the probability of x is unaffected by y, so knowing the probability of y is irrelevant. It doesn't tell me anything about the outcome. In our notation, that vertical line there means given. So we read the probability of A given B is equal to just the probability of A. If we're talking about sports events, then though you may have trouble convincing a fan about this, the probability of their favorite sports team winning is probably irrelevant to their choice about wearing the sports team's jersey. You may not be able to persuade everybody in that. This is partly why statisticians have a reputation of being no damn fun. But setting aside the emotional impact of the fun, these are independent events. One is irrelevant to the other. Now, perhaps if you're talking about very small children playing a game, maybe the probability of a parent being there cheering for the kid, perhaps that's not irrelevant. But for pros, however hard people cheer, there's not too much of a difference. But to begin, I'll assume these are independent. So here x takes the value 1 with 60% probability, x takes the value 2 with 40% probability, y takes the value 1, 2, or 3 with probabilities 50%, 30%, and 20%. Assuming independence, the probability of each of those particular cells is the multiplication. Probability of getting, say, x equals 2 and y equals 3 is going to be 8%, because that's 40% times 20%. Simple math. But how would I distinguish these from another case that's not independent? Label these as A and B. Now, A here can take the value of 1 or 2, while B can take the value of 1, 2, or 3. What is now the probability of A equals 2 and B equals 3? Table shows that probability is 0.1, 10%. But how would I distinguish that from previously? Well, one way is to look at the marginal probabilities. The marginal probabilities are calculated by writing in the margins. That's why they're called that. Add the probabilities in the rows or the columns. Write this sum in the margin. That's the marginal probability. That's where you write them. That's what they're called. On the left-hand side, I have the XY example. On the right-hand side, I have the AB example. The XY example is independent. The AB example is not independent. To see that, you calculate the marginals. Add up the probabilities horizontally. So if y equals 1, then x equals 1 with probability 30%, x equals 2 with probability 20%, so the sum is 50%. Do that again for those other horizontal sums. You could do the vertical sums as well. X equals 1, then y can take any of 3 values, add up those to get 60%. If x equals 2, the sum is 40%. There on the right-hand side with A and B, we calculate the marginal values. So the row sums are 38, 35, and 27%, while column sums are 65 and 35%. Let's talk about how to interpret those so you can understand what independence means. Probability of A equals 1 is in total 65%, because there are 3 different ways or 3 different places where A is going to equal 1. So what's the probability of getting A equals 1 along with any value of B? Just add up the probabilities. Probability of A equals 2 is 35%, since that checks out because those got to add to 1. It's always good to check your math. And if they didn't add to 1, then you made a mistake, because it's supposed to be an exhaustive list of all the possible things that could happen. Going back to our games analogy from the previous lecture, we said we're going to assume there's no such thing as a tie game, because that keeps it simple. If they're tied games, then we just have another column there. These marginal probabilities do not add up to 1. That's a flag that something's gone wrong in the little model. Finally, note for the XY model on the left, the probability in the center boxes is equal to the product of the 2 marginals. For instance, the probability of x equals 2 and y equals 1 is 0.4 times 0.5, which equals 0.2. That's because x and y are independent. That's not the case in the AB table. So that distinction is how we would tell. Now the next steps, once we calculate our marginal probabilities, is find the conditional probabilities. Find the conditional probabilities, we divide each value of the joint distribution by the marginal. Suppose we want to find the conditional distribution of the values of B, conditional on A equals 1. There's a 65% chance of A equals 1, so the probability of B equals 1, given that A equals 1, is calculated as 25% divided by 65%, which is 0.3846. Yeah, I didn't do that in my head. Probability of B equals 2, given that A equals 1, was 0.23. Divide 23 by 65, that's 0.3538. And the joint probability of A equals 1 and B equals 3, 17%, divide 17% by 65%, get 26.15%. So, you just work through and you calculate the different conditional probabilities here. Can do the same thing conditional on A equals 2. What are the probabilities of different outcomes? B, just do those simple calculations, and those are different numbers. They're not equal to the marginals. They're not equal to each other. These are not independent events. Note a little bit of algebraic notation. We use that vertical bar to mean given that. What is the probability of B given that A equals 1? If we were to do these conditional calculations for the XY table, you would find very boring. These conditional probabilities are all equal to the marginal probabilities. So, you can do the boring arithmetic on your own time if you'd prefer, or you can just trust me that that's how it goes, and that's how I cooked up the example. Let's go through a somewhat more interesting example. This is PUMS data from the census. Got information on somebody's highest level of educational attainment. Those are the columns. And then income from salary and wages, that's rows. We ask, are these statistically independent? Which is equivalently asking, does a person's income depend on their education? Now you're probably answering something like, duh, but this is an example of how we think like a statistician. Ask, well, how would I know I were wrong? The first step is get probabilities, so divide the number of observations in each box by the total number of people in the sample. That's the top version of the table. Next, calculate the marginals, adding up the probabilities by rows and by columns. Then calculate conditional probabilities, either looking by rows or by columns. The way to read this, for instance, look at the table where we divide it by rows, so it's conditional on somebody's wage. Conditional on a person making less than $10,000 a year. 19 people in that group have no high school diploma. 39% have just a high school diploma. 20% have some college. 12.7 have a bachelor's degree, and 9.2 have an advanced degree. Compare those with the bottom row. Conditional on a person making more than $100,000. People with an advanced degree make up 44.9%. The other way of looking at it, divided by columns, asks the question, conditional on a certain educational qualification, what are the probabilities of different wages? Let's say a person has just a high school diploma. Of the people with that qualification in the sample with just a high school diploma, 58.6% make less than $10,000 a year, 30.2% make $10,000 to $50,000 a year, 9.4% make $50,000 to $100,000 a year, and just 1.8% make more than $100,000 a year. Compare that to people with advanced degrees, where 21.8% make more than $100,000 a year. So, you can kind of see and get the distinction there. Now to finish up with some of the equations, what we're doing here, just to show the general case, the probability of A given that event B happens, that's the probability of A and B both happening, divided by the probability of B happening. That's how we define conditional probability. We can swap A and B, so the probability of B given A is the probability of A and B combined happening, divided by the probability of A. Putting together those two equations on the top, do a little bit of substitution, a bit of algebra, get what's known as Bayes' theorem. The probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. We'll come back to some of the ways in which that's useful for understanding the world, but for now it just comes right out of the definitions.